Okay. All right. So where were we? We were somewhere around here. So we finished talking about the cyclopentadienyl anion right here. Hopefully you can all see that. I'll give it a second here. My computer's a little slow. Yeah, so we talked about the cyclopentadienyl anion. I asked you to memorize that. It explains why cyclopentadiene is such an acidic compound, because when you abstract a proton, it becomes an aromatic anion. Then we talked about the tropylium cation, and we explained why it is an aromatic cation, and that is a severed membered ring. And we explained that in terms of frost circles and in terms of a continuous overlapping system of p orbitals. And so now we're going to switch gears and we're going to talk a little bit more about aromatic heterocycles. And the one that you would be familiar with so far would be pyridine. Right, this would have been introduced at the very beginning of Chemistry 3101. And I think it's in chapter 1 that we talk about that compound. And we talk about how in pyridine, you have 1, 2, 3 pi bonds in the molecule. And so that begs the question, what kind of orbital is the lone pair on the nitrogen sitting in? And you can see here that if this nitrogen has a steric number equal to 3, it is sp2 hybridized, but you know that one of the p orbitals on the nitrogen is already being used to make this pi bond, right? So we could say here, p orbital used to make this bond, okay? And so what does that tell you? It tells you that the lone pair is not in the p orbital, it's in an sp2 hybridized orbital. And so if that nitrogen becomes protonated, okay, you go from pyridine, which is aromatic. If it was to gain a proton and form a pyridinium anion, or sorry, a pyridinium cation, it would look like this, okay? And this compound would still be aromatic, right? You haven't touched anything to do with the the 6 p orbitals that are overlapping. And so pyridine is a base. Pyridine is basic. Okay, why? Because even when it gains a proton, it's still aromatic. Whereas pyrrole, on the other hand, it turns out that the lone pair on this nitrogen is in a p orbital. Why would this be in a p orbital? Okay, you probably look at this initially. You probably look at this initially and say, well, that nitrogen has a steric number equal to 4, therefore it's sp3 hybridized. Well, it turns out that's not true, okay? It's not sp3 hybridized. Why not? Because if that lone pair goes into a p orbital, then we have a continuously overlapping system of p orbitals, okay? And then we have a total of 1, 2, 3, 4, 5, 6 pi electrons. So we would have a Huckel number of pi electrons. And so pyrrole is aromatic, but the lone pair on the nitrogen is required for aromaticity. And so that's why pyrrole is not a base. So I know it erased what I had written before, but we'll put pyridine is basic, and then we'll put here pyrrole not basic. Okay, it is not a base. Okay, and you see that manifested here. Okay, when pyridine, I don't need to write the names in. When pyridine picks up a proton, it's still aromatic, whereas when pyrrole picks up a proton, it becomes non-aromatic. And so when pyrrole gets protonated, it's going to be a lot more acidic. Why? Because it wants to get rid of this proton. It wants to go in this direction so that it can become aromatic again. So you will restore aromaticity. So again, to review, pyridine is an aromatic compound. Pyrrole is an aromatic compound. When pyridine is protonated, it is still an aromatic compound, but when pyrrole gets protonated, it is a non-aromatic compound, like that. All right, so aromatic heterocycles, pyrrole and pyridine. You can see the difference between the two lone pairs when we look at an electrostatic potential map of the two of them, the EPMs. So these are called electrostatic potential maps, okay? And you can see that the lone pair on the nitrogen in pyridine is localized, whereas the lone pair on pyrrole is delocalized throughout the entire ring. And so again, this lone pair is localized, so it is basic, whereas this lone pair is delocalized, so it is non-basic. Okay? And if you have to memorize these specific examples, do it. If you understand the rationale, that's great. But if you have to just memorize them, that will work too. It will get you to the right answer. So the next question, or this question, 17.11, just says, are these compounds aromatic? So we'll use A for aromatic. Non-aromatic, we'll use Na, or anti-aromatic, we'll use double A for that. So it's asking us about each one of these. Are these compounds aromatic, non-aromatic, or anti-aromatic? So if we take a look at the first one, okay, we have a continuously overlapping system, or we could have a continuously overlapping system of p orbitals, right? If this lone pair went into a p orbital, we have a p orbital here and a p orbital here. So would that fit the criteria for being aromatic? The answer is yes. Okay, it would fit the criteria for being aromatic because we do have a continuously overlapping system of p orbitals. However, do we have a Huckel number of electrons? So let's think about this. We have a total of, I'll use my red pen, 1, 2, 3, 4. That is not a Huckel number. That's an even number of pairs. So this satisfies not 4n plus 2, but it satisfies 4n, where n is equal to 1, right? If you take 4 times 1, what do you get? You have 4. And we have a total of 4 electrons here. And so this would be anti-aromatic. Okay, this would be highly unstable. Okay, so if we take a look at the next one, okay, let's try one more, and then I'll let you guys try the rest before class on Wednesday. If I look at this carbocation, that carbocation is definitely sp2 hybridized. So we have a p orbital on it. We have one here, and we have one here, because these two carbons are sp2 hybridized. So we have a continuously overlapping system of p orbitals. So that's good. But then how many electrons do we have in our continuously overlapping system of p orbitals? We have 1, 2. So this satisfies 4n plus 2 when n is equal to 0. 4 times 0 is 0, plus 2 gives you 2. So that means that this cation would be aromatic. Okay, so what I want you guys to do before class on Wednesday is I want you to try both of these for class on the 29th. Okay, I want everybody to try these and try them without looking at the solutions manual first, and then we'll walk through the solutions of all of these two together. The same thing for these ones here. Okay, I want you to try these before class on Wednesday, but I do want to take a look at the first one with you. Okay, so if you look at this oxygen has a steric number of 4, right? Just like the oxygen in water. It's got 2 single bonds and 2 lone pairs. So you might think that this oxygen must be sp3 hybridized. Well, remember, an atom will do whatever it has to do to make the compound aromatic. So if this atom were to take on sp2 hybridization, that would mean that one of the lone pairs would go into a p orbital. So then we would have 1, 2, 3, 4, 5 p orbitals, and we would have a continuously overlapping system of p orbitals if the lone pair goes into a p orbital. So would it happen? The answer is yes, it would happen, because if it did go into a p orbital, then we would have a total of 1, 2, 3, 4, 5, 6 pi electrons. That is a Huckel number, 4n plus 1, when n is equal to 1. 4n plus 2 when n is equal to 1. 4 times 1 is 4, plus 2 is 6. So that means that this compound is aromatic. Okay, this compound would be aromatic. So I want you to take a look at the rest of these. I want you to take a look at the rest of these by May 29th, and we'll cover these at the beginning of class on Wednesday afternoon. Polycyclic aromatic hydrocarbons, or polycyclic aromatic compounds, I'm not going to go into a lot of detail about these. These compounds are actually poisons. They're found in things like cigarette smoke. But I would recommend memorizing the names of naphthalene and anthracene. And something that's cool about these aromatic compounds is in anthracene, for example, the ring in the center, okay, this ring is more reactive than outer rings. All right, so that's kind of interesting, but really we don't go into a lot of details on those. Here it talks about the heats of energy of these compounds and how they're less stable than benzene. But again, I'm not going to quiz you on that, so don't worry about that one. All right, 17.6 is pertinent, and I do want to cover some of this information with you today. So it says, a carbon directly attached to the benzene ring, that position, we call it a benzylic position, okay? So if you have an aromatic ring, a benzene ring, okay, here's your benzene ring, a carbon attached directly to it is called a benzylic carbon, and we call that position the benzylic position. So we have a benzylic carbon here, and we have a benzylic carbon here. Now, you guys remember this reagent here? This is what I call the Jones reagent. Jones reagent. It's just a very strong oxidizing agent. It's a way of making chromic acid, H2CrO4, is you just mix up sodium dichromate, sulfuric acid, and water. Well, if you take benzene and you treat it with chromic acid, nothing happens. And if you take an alkane and treat it with chromic acid, you get no reaction. Okay, nothing happens whatsoever. However, if you have an aromatic ring with a benzylic position on it, okay, and notice that the benzylic position on this molecule has two hydrogens. There's one here and one here. So you would just call this butylbenzene, okay? If you treat that with the chromic acid, then what it does is it oxidizes the carbon at the benzylic position all the way to a carboxylic acid. And if you're wondering what the heck happens to the rest of the molecule, where does that go? It just says it's excised, okay? So that just means it ends up in the waste in the end, okay? So it just kind of goes away when you work the reaction out. So you oxidize the benzylic position. However, there's a caveat to this. You have to have at least one proton. Benzylic position needs to have at least one proton attached you have to have one proton at the benzylic position. And so since there is no proton on this compound, which is tert-butylbenzene, you get no reaction. So besides using chromic acid, we can also use permanganate. Now, if you use permanganate, it's a two-step process. The first step is using potassium permanganate, water, and heat. And the second step is using aqueous acid. And the reason why you have to do that is because you form this salt, okay? This compound would be called potassium benzoate, but it's because you end up with the benzoate salt, and then you have to protonate that with acid to produce the conjugate acid. All right, so there you go. So there's two possibilities. Again, number one, okay, so we have these conditions, or you can use the chromic acid conditions. Okay, so sodium dichromate. Sorry, you guys, my iPad's acting funny. Sulfuric acid and water, like that. All right. So benzylic positions is kind of like allylic positions that we looked at before in the class, where it can undergo a radical-free bromination. So if you have a benzylic proton, okay, you can treat the compound with NBS, so that's N-bromosuccinimide, and heat, and that will brominate at the benzylic position. And it turns out that benzylic bromides, whether it's tertiary like this one, or if it's primary, so let's say you had something like this, son of a gun, that's the ugliest aromatic ring I've ever seen in my life. If you have something that's primary, like this, okay, like that, still not much better. Okay, something that's primary, those are going to be great intermediates in synthesis, and let me show you what I mean. You guys know the SN1 reaction in detail, right? If I have a tertiary benzylic bromide, right? We know that if we treat that with solvolysis condition, so this is, if you remember, this is called solvolysis, okay? It's going to form a tertiary benzylic carbocation. Water is going to come as a nucleophile. Then we get a proton transfer, and then we get a tertiary alcohol. So we go from a tertiary alkyl bromide to a tertiary alcohol. If you have a primary benzylic bromide, like this one here, is this primary, that can undergo an SN2 with sodium hydroxide, like you have seen here. And then we form a primary alcohol. So this compound, this is called benzyl bromide. Benzyl bromide. And this one here is called benzyl alcohol. Benzyl alcohol. The reason I bring them up is because the names up is because they show up so much as we move forward in the class that I might use the word benzyl bromide here and there. All right. What else can you do with a tertiary alkyl bromide? Well, you guys know E2 reactions, right? If you take this and you treat it with a base. So if we take this compound and we treat it with a base, you guys know that we could abstract a proton like this with our ethoxide. So if we just draw a quick mechanism, it's going to look like this. We're going to pick off the proton, form the double bond, lose the leaving group like that. Or you could do my favorite reaction, which is just heat up your alcohol and acid, and that's going to give you the Zaitsev alkene, which we have shown here. So there's a lot of power in this idea of benzylic oxidation and radical bromination. So what have we covered? We've covered that you can take the benzylic position and you can oxidize it to a carboxylic acid. But remember, you have to have at least one proton. Okay, you've got to have at least one proton at your benzylic position or it doesn't work. Then we said if you have a primary, or sorry, if you have a benzylic position, you can also do radical bromination with NBS and heat. So NBS and heat. And if you have a primary benzyl bromide, you can do an SN1 or an SN2. If you have tertiary, you can do an SN1. You can make alcohols. And then that really opens up, Pandora's box again. You can do all the reactions of alcohols and all the different reactions of alkenes that you would have learned in this class. So there's a lot of chemistry there. So this question, which we're going to finish on Wednesday, just asked you, what would happen if each of these compounds was treated with chromic acid? So remember, we make that from sodium dichromate, sulfuric acid, and water. Well, here we have a benzylic position and we have a proton. So in this case, we would end up with benzoic acid, right? It's going to excise the rest of the molecule. Actually, there is none to excise here. If you look at this one here, we have a benzylic proton here, and we have a benzylic proton here. So what's going to happen with our same old conditions? Let me just copy them and paste them like this. And what we're going to end up with in this case is we're going to end up with a dicarboxylic acid. So I'll just write it the condensed form, CO2H, CO2H, like this. I can make this bond a little prettier. That didn't help, did it? There we go. All right, and we'll leave this one, this last one. We'll save this one for Wednesday's class. All right, and then the last thing I wanted to cover with you today is the reduction of benzene. You guys know hydrogenation reactions very, very well. If you were to take a compound like 1-butene, okay, and if you're to treat that with hydrogen gas and platinum, right, that's going to hydrogenate to give you butane. You might be wondering, can I hydrogenate benzene? Well, we talked about it a few minutes ago, and I said yes. If you use high pressure and high heat, yes, you can hydrogenate benzene, and it releases, 208 kilojoules per mole of energy. But if you have a double bond outside of your aromatic ring, like we see down here with styrene, so it turns out that you can, so this is called a vinyl group. So you can hydrogenate just the vinyl group at low pressure and low temperature. So you can do a selective reduction of something that is more easily hydrogenated outside of your aromatic ring. Now there's another type of reduction you can do, which is called a Birch reduction. And for the Birch reduction, so Birch reduction, you need sodium and methanol, and you need ammonia. Okay, these conditions together make up what we call the Birch reduction. So the Birch reduction. And you can see that the Birch reduction converts benzene into some kind of derivative of 1,4-cyclohexadiene, like that. And it turns out that the mechanism is very similar to the dissolving metal reduction of an alkyne that we saw earlier on in the class. You guys know that sodium, right? Sodium has it has one s electron, right? So if I draw the Lewis structure of sodium, it's just this. So it has one s electron to give up. And so if it gives it up, it forms what's called a radical anion. Notice that the radical anion has a radical, and then it also has an anion. And I want you to remember that, because after it it accepts a proton from the methanol, another atom of sodium donates another electron, and you end up with another anion. So we form an anion again. And that is relevant because we don't completely reduce the benzene ring. We produce two sp3 hybridized carbons. Depending on where the substituents are, we can figure out which carbons are going to be reduced. So it turns out that if you have an electron donating group, so if you have an electron donating alkyl side group, we call this an electron donating group, so something that donates electrons, it turns out that that is not going to be reduced. Now, why would that be? The reason why it's not going to reduce the carbon where the electron donating group is at is because you form an anion along the way. So why would you donate electrons to something that's going to form an anion anyway? So you want to memorize that when you have an electron donating group, that carbon is not going to be reduced. However, what if you have an electron withdrawing group, right? If you have an EWG, okay, if you have an electron withdrawing group, then that carbon is going to be reduced. Why? Because you have an electron withdrawing group, and it's okay with having a carbanion there, right? It's okay with a negative charge. It can accommodate it. And so I'm never going to ask you to draw this mechanism. So if we go back here, you will not be asked to draw, okay? Will not ask. I'm not going to ask you to draw that mechanism. However, it's wise to know what the radical anion is, because it will provide you with a good rationale for understanding why electron donating groups, their carbons are not reduced, whereas the carbons with electron withdrawing groups, those are reduced. Okay? And so with that in mind, what we'll do on Wednesday is we're going to take a look at these problems. Okay, you can see the first one involves a benzylic bromination, right? If we take toluene, right? If we just take toluene, and we treat that with NBS and heat, that's going to make benzyl bromide like this. And then if we hit that with sodium cyanide, right, the cyanide is going to act as a nucleophile, and we're going to end up with our product. Okay, I'm kind of running out of space here, but I'll just put it here like this. Okay, so I want you to try these two, and we're going to take a look at them at the next class, and then we'll also take a brief peek at the spectroscopy of aromatic compounds. And that covers the entire chapter. Okay, these are all things that you would have seen, the spectroscopy of aromatic compounds. So there's nothing new in here whatsoever. The part about buckyballs, I'll leave that as an FYI. The part about nanotubes, I'll leave that as an FYI. And so we've essentially covered the entire chapter today. Sorry, you guys, I don't know what you did to my iPad, but it's acting really funny now. So I sincerely apologize for that.